Join us on a voyage through the wormhole, your gateway to groundbreaking thinking on AI, space exploration, a healthy planet, and a more intelligent future. I'm your host, Jonathan Knowles.
The Wormhole is produced by Trillium Technologies, leading the application of artificial intelligence for planetary stewardship, space exploration, and human health. Help us explore what's over the event horizon by following us on LinkedIn and Twitter at trillium.tech. Together, let's build an intelligent future.
Thank you for joining us as we explore the domain of heliophysics in this Wormhole series. NASA has designated 2024 as Heliophysics Big Year, and we are featuring scientists who are at the forefront of unraveling the mysteries of our very own star, the Sun, and its profound effects on space weather and Earth's climate. At FDL, we have been engaged in heliophysics research for 7 years, so we are so fortunate to hear from these scientists, all of them FDL faculty who bring a wealth of knowledge and experience, as well as their groundbreaking research, which has significantly advanced our understanding of solar phenomena and their impact on the solar system. This series is produced by Trillium Technologies, and FDL is a public-private partnership with both NASA and the ESA. Let's begin by introducing our guest today, my good friend and colleague, Dr. Tom Berger. He's the director of the Space Weather Technology Research and Education Center at the University of Colorado Boulder, and he has recently become one of the first principal investigators in NASA's new Space Weather Centers for Excellence program, working with NASA and NOAA and the university partners to develop the next generation of orbital space weather forecasting models. He came to space weather research via a lifelong love of astronomy and physics. He's a graduate of UC Berkeley with a degree in engineering physics, followed by a Ph.D. in applied physics and astrophysics from Stanford. He also founded the Space Weather Deep Learning Laboratory, the first university facility to focus on AI/ML applications to space weather prediction. He has been a faculty member of FDL since 2021, working with teams of researchers to develop advanced models for prediction of the low Earth orbit environment, which is a critical region of space that is particularly vulnerable to extreme geomagnetic storms created by, or triggered by, I should say, solar eruptions. Tom, it's always good to see you, my friend. Welcome to the Wormhole. How are things? Let me ask you this: How's the weather in Boulder?
It's beautiful, Jonathan. Thank you for having me.
No, Tom. How's the space weather in Boulder?
As it is everywhere on Earth, it's not too bad right now. We're having a little calm period after that earlier storm this week from AR 3516, as you might have seen.
Yeah, as a matter of fact, it's right there in the background. That's AR 3516, an image I captured just a couple of days ago, right after the double CME that we had. And we'll talk more about that in a little bit. But let's get started by talking a little bit about your journey. We talked about the highlights in the introduction here briefly, but tell us about your journey into a career in the science of heliophysics and space weather, because I know from experience there are not a whole lot of people who take that path. What was your path like?
Yeah, well, as you mentioned, I have a lifelong interest in astronomy, and I also had a lifelong interest in aeronautical engineering. And so those two things sort of combined for me in graduate school serendipitously. I was actually at the time studying high temperature gas dynamics and supersonic combustion, and in my interest in aviation propulsion. And I started getting more interested in plasmas as the hottest and ionized form of gas, and was studying plasma dynamics and came to realize that the most interesting plasma system in the universe, in my opinion, is our sun. And at that point, I thought, well, this is so interesting that I might shift over to the astronomy astrophysics track. And that's how it all started a long time ago at Stanford. So it really was a convergence of, looking at the physics of high temperature gases as they get ionized and being fascinated with the magnetic field effects on these plasmas that led me to solar physics first. And then I had a career in solar physics for about 20, 25 years when I began to see that I was sort of focused on the sun and really studying just the magnetic field generation and diffusion on the sun. And then I began to realize that these eruptions that I was seeing occasionally from my ground-based telescope observations were really consequential to the Earth. And that sort of led me to kind of widen the lens, if you will, and start looking at the impact of the sun on the Earth as a system. And that sun-Earth system science was just so fascinating to me. And so there was such a richness there of physics, not only with the fully ionized plasma physics of the sun and the eruptions on the sun, but the transport through the interplanetary space of the plasma after the eruptions, the interaction with the Earth's neutral and partially ionized atmosphere, the magnetosphere. All of these things kind of came together for me as a fascinating subject in and of itself. And I've been sort of a space weather physicist, if you will, since about 2012, 2014, when I came to Boulder, actually.
And it's my experience that very few people have heard the phrase space weather at all. More and more, perhaps, as it begins to show up a little more, as we have gone from dozens to hundreds to thousands of satellites in low Earth orbit. Perhaps you can explain a little bit about what space weather is and why it's important for us to understand its effects on Earth and our activities as humans.
Yeah, I like to look at it as sort of in the broader view, sort of a stellar planetary interaction science. And if we narrow into our particular solar system, it's really the Sun-Earth system that is the most relevant here, although the Sun, Moon, and Sun, Mars are becoming more relevant in these times. But it's really a study of the interactions of the sun with the Earth and how the solar output influences both the Earth's upper atmosphere, its magnetic field, and ultimately all the way down to the ground because of the magnetic field interactions that the sun unleashes on the Earth, if you will, through its solar wind, which is a magnetized plasma continually flowing from the sun, or from these eruptions, these flares that I talked about earlier, that can unleash giant clouds of really magnetized plasma, which, if they happen to impact the Earth, can cause what we call geomagnetic storms on the Earth. And those geomagnetic storms can lead to impacts on both the natural system of the Earth, which then cascade down to impacts to technological systems operating either on the surface of the Earth or, as you noted, particularly more and more in space. And one of the biggest impacts that we look to these days, and we're trying to do a better job at predicting and characterizing, is the impact of these solar storms, if you will, on the magnetic field of the Earth, generating gigantic electrical currents within the ionized region of the Earth's atmosphere, the ionosphere, sort of the layer above the stratosphere and the mesosphere, starting around 100 kilometers, the edge of space, if you will. During a large solar outburst, you can get very, very large electrical currents surging through the ionosphere and also depositing field particles, really, and plasma into the polar regions of the Earth's magnetic field, which cause the aurora, the most visible aspect of space weather. But these currents, these electrical currents in the ionosphere, actually can heat up the upper atmosphere of the Earth, the thermosphere as we call it, because it's hot. And so the thermosphere gets even hotter during space weather events. It then swells up, essentially becoming more dense than it normally is. And satellites flying in low Earth orbit from altitudes, say around 200 to 1,000 kilometers, maybe 1,200 kilometers, will actually feel that additional atmospheric density from the space weather event as drag on the satellite. And drag on the satellite decreases the energy of the satellite, pulling it down into the gravity well more than it normally would be. And it actually speeds up as it does so. So all of a sudden, during a major event, a lot of satellites in low Earth orbit are not where they're supposed to be. And as we get more and more crowded up there, as you mentioned, it's really critical that satellites maintain their orbits, both altitude and in track positions, within a few kilometers, really. And during a large event, what we worry about is we can have movements of tens to hundreds of meters, maybe even several kilometers in altitude and or in track motion, depending on the severity of these space weather storms. So it becomes a real technological impact issue, not just a phenomenological impact issue when you're talking about space weather impacts in near-Earth space.
Now, in just a moment, I want to ask you about something that you've recently published, a paper, a new journal that I think is very exciting. But before we do that, let's talk just briefly about a couple of the sort of more significant events that happen on the sun. Because going back to your journey, of course, the sun has been full of so many mysteries for all of humankind, to the point where we've built entire cultures and religions around it. And it still is full of mysteries. That said, we've learned a lot, but there are two things in particular that it does that are big triggers of things. One are solar flares, of course, and the other are coronal mass ejections. If you could just briefly tell us what each of those are and how they're different.
Well, actually, I like to say that they're actually unified into a single event, which is called a solar magnetic eruption. So what happens is you get sunspots on the sun, like the ones behind you on the sun there. What those are intense magnetic fields concentrated by the motions of the plasma on the surface of the sun into these dark sunspots. Those intense magnetic fields can interact with each other, especially if they're opposite polarities, and they can cause these giant magnetic eruptions. It's essentially a slow buildup as the sunspots grow in size and complexity and move around. The slow buildup is essentially injecting energy into this magnetic system over a course of, tens of hours to days. And then at some point, which we don't understand yet, we don't understand the triggering events, we don't understand how solar eruptions become so large in some cases. But at some point, there's a triggering that releases that built up magnetic energy from the sunspot interactions. That's the eruption. That eruption is what explodes this plasma cloud out into space, causing the coronal mass ejection. It's also that eruption which ejects plasma downward and energetic particles like protons and electrons downward into the atmosphere of the sun, causing the flare. So there's suddenly, heating to 20 million, 30 million, 100 million degrees of the plasma on the surface of the sun, which normally sits around 5,000 to 10,000 degrees. That 100 million degree plasma emits X-rays, gamma rays, all the way through the radio spectrum. It's a full spectrum event. And we call that the solar flare. So they're really, the flare and the CME are, generated by the same underlying root event, this magnetic eruption. And then in addition, the CME, as it plows through interplanetary space, is accelerating. It's essentially a big shock wave plowing through interplanetary space and the outer solar atmosphere of the corona. It's accelerating the protons in particular that are out there, sort of free protons in the plasma of the corona. Those protons can be accelerated to relativistic energies, causing what we call the radiation storm ahead of a CME. So it's sort of a three-pronged, a three-punch hit, if you will, from a magnetic eruption, all originating with that magnetic field eruption, causing the flare, the CME, and the CME pushing through the atmosphere, causing a big radiation storm, which is one of the main things we worry about for people outside the protective magnetosphere and atmosphere of Earth. That radiation normally is deflected by our magnetic field, doesn't penetrate the atmosphere very much. But if you're in a spacecraft, in deep space in particular, that is that's your biggest threat from space weather, really.
And no, the timings are different for these things. It's not just light travels at 186,000 miles per second. It's more complex, more nuanced than that, isn't it?
Yeah, I mean, we see the flare first because the photons do come out at the speed of light, and the plasma's traveling at a fraction of the speed of light. Those energetic particles associated with the CME, though, are accelerated to near light speed. So you can get near light speed protons coming to Earth within 10 to 15 minutes of the eruption. And so that's one of the most critical things we need to be able to predict better than we can today is that particular eruption going to cause a radiation event that's going to be in the direction of astronauts in space. And we can give them sort of a 15-minute warning right now at most. We'd like to give them more. We'd like to say that sunspot group is going to erupt definitively, we're pretty certain it's going to erupt, say, with a 70% chance of eruption in the next 12 hours to give people, particularly in deep space, time to prepare for these events.
We're still it's a bit like weather forecasting in that sense,
Yeah.
isn't it? I mean, the one that just hit day before yesterday, it's a significant one. Two, it was a double CME out of the spot that you see here in the image behind me. And it hit almost 18 hours before the original prediction said it was likely to hit the Earth. A bit like rain. Oh, it'll rain tonight at 5, and maybe the rain comes in at 3, or maybe it doesn't come in till 7, at least with our forecasts today. And it's because we're modeling this, aren't we?
Yeah, and that brings up a really key point that I like to emphasize too, is that space weather is not just about the phenomenon. It's not just about the impact. It's about predicting these both phenomenon and impact. And so that, in that sense, that's really why we call it space weather, just in that exact analogy with terrestrial weather or ground-based weather, if you want to call it that. It's the same problem. We need to be able to predict these things with high accuracy and reliability. And we do that with models and data. And unfortunately, we're quite far behind. If you think your weather forecast down here on the ground is bad, the space weather forecasts are really challenged because we have far less data. We have models that are still struggling to capture all the physics involved. And it's a much bigger system. You've got magnetic fields and plasmas, not just neutral gas and water, for instance. And so it's a much more complicated problem to model these systems, run those models in real time, try to add data in, hopefully, to influence the model output, and produce a reliable and accurate forecast. And we're just not there yet. The CME arrival times, as you note, are at best sort of plus or minus 12 hours, which...
Let's come back and talk a little more about prediction in a minute. But real quick, before we take a brief break, if you could just very quickly tell us about this new journal that is focused on this, and we'll share a link. And I apologize, I don't have that handy, but I'll try to get that over to Catherine for the paper that you just published that talks about the inaugural issue of this journal.
Yeah, this is the Journal of Geophysical Research, JGR, Machine Learning and Computation. It's the first journal in the AGU pantheon of journals to focus on machine learning and computational data-driven methods for essentially Earth and space sciences. And we just had our inaugural issue that was composed of an editorial kind of explaining why the editorial board, which I'm on, feels that now is the time to have a journal discussing this, what we think is the revolution in how science is done and will be done in the coming decades.
This really speaks to just how new this science is in some ways. Certainly, we've been looking at the sun for hundreds of years. However, it's really coming into its own now, and I think as evidenced by this new journal.
Yeah.
Oh, look, and it's in the chat. They found it and they got it. Well, I tell you what, let's do this. We're going to take a short break and come back in just a few minutes, just not even a few minutes, about 30 seconds. So those of you who are with us, please stay with us. We are here with Dr. Tom Berger, the director of the University of Colorado Space Weather Center. Come on back and join in us a couple minutes. We'll continue. We're back with Dr. Tom Berger. We're talking today about space weather, and I'd like to spend a little time, Tom, continuing the conversation about prediction and monitoring and looking at some of our current capabilities and what are some of our limitations in predicting space weather. How are we really monitoring the sun's activities? It's just such a big thing. We do have some ground-based and space-based ways of doing that, but talk to us a little bit about capabilities and limitations, please.
Yeah, as you mentioned, there's several ways that we monitor the sun 24/7. We've got ground-based telescopes, we've got space-based telescopes. The main thing we need to do, and there's a lot of improvement here, or a lot of room for improvement, the main thing we need to do is monitor the magnetic field of the sun. So the sunspot picture that you have behind you is really what you'd see by eye with a proper filter over a solar telescope, and you can see the sunspots. but you can't see the magnetic field polarities of the sunspots there. And therefore, the telescopes we use for space weather monitoring are really focused on measuring the magnetic field so we can see where the positive and negative polarities are coming together, becoming complex, building up that energy to eruption, and giving us perhaps some chance of warning people about the coming flare effects, the CME effects, and the radiation effects that we talked about earlier. So it's really about monitoring the magnetic field. Now, that said, the telescopes around on the ground here can monitor the magnetic field on the surface by looking at visible light in spectroscopic methods. But really, what we need to be monitoring more and more, we think, are the magnetic fields in the upper atmosphere of the sun, the corona, that part of the sun that you see during an eclipse, for instance. And you can't really see that from the ground for various reasons. We don't have very many eclipses, for one. Specialized telescopes can look at it, make an artificial eclipse, but it's very challenging to get accurate magnetic field measurements in the outer atmosphere of the sun with a coronagraph, as we call it. So we really need to go into space to both get higher resolution, get out from below the swimming pool of the Earth's atmosphere, which plays havoc with all kinds of spatial resolution issues and with telescopes on the ground. You get out into space, and we have several space telescopes, including sort of the premier one being NASA's Solar Dynamics Observatory. And that allows you to then not only measure the magnetic field of the sun on the surface with higher precision and spatial resolution, but you can see the corona, the extreme ultraviolet emissions from the corona of the sun and the chromosphere, that upper sort of middle atmosphere of the sun, if you will, directly. So now you're starting to be able to see the activity of those flows building up the energy towards the magnetic eruption from the space telescopes. One of the problems we're having, though, is we only have this one view from Earth. So from Earth, with a space telescope or a ground-based telescope, you're really only looking at sort of one side of the sphere. Not only that, the magnetic field measurements are really, to get them to be accurate enough, you really restricted to about a third of that front side. You can't really measure magnetic fields accurately towards the limb. And so one of the biggest challenges we face going forward is trying to monitor more of the sun. And the Europeans have a mission. They're planning to fly to the L5 Lagrange point, which is a gravitational balance point about 60 degrees sort of eastward, if you will, around the east side of the sun, the left side of the sun, if you're looking at it. They're going to plant a spacecraft out there to give us a little bit more view of that part of the sun, which is rotating around towards the Earth. That's great. We really, though, need to see the poles of the sun, because it turns out the poles are where you have a lot of magnetic activity, which structures that coronal atmosphere we talked about earlier, which then influences how CMEs and the solar wind propagate through the interplanetary space. And right now, we've got models that just assume what the polar fields are. There's very rough, extrapolations from what we can measure from the lower latitudes of the sun. All of these are insufficient to really give us a good look at the polar fields of the sun, which we could then feed into models, which would give us a more accurate look at how the solar wind is coming out and how those CMEs are going to propagate once they explode off the surface of the sun. So we're really hoping to get polar views as well as views all the way around the sun. It's a 4 pi steradian view of the sun, if you will, is what we're really is the sort of the holy grail of solar physics and space weather monitoring. Because it makes sense, if you're a spacefaring nation in particular, you want to monitor your star. Your central star is what's causing all of the problems out there in terms of the environment. And just looking at one piece of it at any given time is not enough. It'd be the equivalent of looking at just one side of the Earth and trying to forecast the weather, the global weather situation. That's why we have weather satellites around the entire Earth looking at it 24/7. That's what you need to successfully forecast the environment.
So we need the same thing for our star.
That's right.
As a matter of fact, on our next episode in this series, we'll be interviewing Dr. Anna Jungbluth from the European Space Agency. She is one of the faculty members at FDL, and we will be talking about the sun's role on Earth's climate as a thing. Now, all the things that you just said, of course, fit nicely into what we do at FDL, the notion of applying AI, specifically ML, to help figure out some of these things that we're talking about. And those who do AI research like we do know that ML is very good at predicting things. It's an exciting, I have to believe for you especially, a very exciting field to be at the intersection of AI, ML, and heliophysics.
Absolutely. I mean, one of the things we're finding is that, again, this is such a complex system that the physics-based models that we have of the sun, the solar wind, the interplanetary space, the Earth's magnetosphere, and even the Earth's upper atmosphere, that mesosphere, ionosphere, thermosphere I talked about earlier, there's so much complex physics going on that the physics-based models really have a hard time locking on to a specific trajectory and phase space, as we say, and predicting what the future of the system is going to be. In contrast, data-driven methods are showing that they can, with enough data available, and thankfully, as I mentioned earlier, NASA's Solar Dynamics Observatory has now given us sort of 20 petabytes plus of data on the sun's atmosphere and magnetic field. Now we can start to have data-driven methods applied to this prediction problem, and we're finding that it is actually producing better predictions than the physics-based models, to use these data-driven machine learning models, if you will. We're not quite there where we can say we've achieved terrestrial weather prediction accuracy and reliability, but there are those of us in this field who think that within 10 years, most of the forecasting models we use for space weather will be data-driven machine learning-based models. If not, highly integrated data-driven and data assimilation methods into the physics-based models to make sure that the physics-based models are at least giving us a correct trajectory in the future of the complex nonlinear system.
This is important stuff. And while we've been observing the sun for hundreds of years, hundreds and hundreds of years, ancient Chinese astronomers were drawing pictures of sunspots on the sun. Of course, Galileo famously, we have his notebooks of the sunspots on the sun. But there have been some events that people didn't know what was going on in the last century and the century before that were fairly significant. You know, I'm a little partial to the 1859 event. You're a little partial to the 1921 event. Tell us about those 2 years and what happened and why that matters for us today.
Yeah, the 1859 event is a favorite, of course, because that was the first time that an astronomer was observing the sun. This was Richard Carrington in England and another astronomer as well. They were doing their daily sunspot observations with visible light telescopes, sketching the sunspots. And in 1859, around August 30th or so, or September 1st, Richard Carrington saw a flare for the first time. And if it's a big enough flare on the sun, it not only emits X-rays and EUV, extreme ultraviolet radiation, which of course doesn't penetrate the atmosphere, can't be seen from the ground, but a big enough flare will also create a visible light flare. And that's what Richard Carrington saw. And he very excitedly reported this. And at the time, people thought, well, that's interesting. Maybe it was something in the Earth's atmosphere you saw. You know, we're not really sure what it was. However, about 17 hours after he saw that flare, the largest geomagnetic storm to ever be recorded by instruments like magnetometers, which were fairly new at the time, but had been around for 100 years or so at least, the magnetometers went off scale and caused the largest geomagnetic storm in the history of recorded geomagnetism. And so a lot of, there were several people, there was Balfour Stewart and Richard Carrington and others who said, well, wait a minute, we just saw this kind of explosion on the sun maybe, and 17 hours later, the geomagnetic field of the Earth went crazy. Maybe there's a connection here. And, as science does, many of the top scientists at the time said, no, you're crazy. That's impossible. There's no way the sun can, it's just photons. It can't actually influence the magnetic field. And so there was a long period where this sort of argument went back and forth as to whether the sun can influence the Earth in this way and cause this geomagnetic storm, which the most visible effect of the 1859 event was the aurora. as is it's the most visible effect of space weather for all events. And in 1859, the aurora was so bright that all the way down in Denver, Colorado, for instance, the story goes that miners were woken up at 3 a.m. thinking that it was sunrise because the sky was completely red. And that's an extremely rare event. So the 1859 geomagnetic storm is known to be one of the largest still to this day. However, in 1921, there was also an extremely large geomagnetic storm caused by a sunspot group that launched several CMEs in a row in about May 14, 15 of 1921. And this was the first time that there was a major technological impact because of space weather. Not only was the aurora visible as it was in 1859 down to very southern latitudes, Denver, Texas, Cuba. In 1921, the aurora was visible in American Samoa, and very close to the equator. So this was, some people believe this was bigger than the Carrington geomagnetic storm. And in the Carrington event in 1859, there were telegraph systems, long wires stretched across the Earth, which picked up this current that is generated in the ionosphere that I talked about. It actually propagates into the ground and gets sucked up into these long conductors, geomagnetically induced currents, we call it. 1859, they had some telegraph interruptions. In 1921, they had major telegraph interruptions. They had major train communication system interruptions. And in fact, there was one telephone exchange in New York on the railroad system that was, the entire building was burned down by a fire caused by these geomagnetically induced currents. So this was the first time that there was also a fire started in Sweden. This was really the first time that people realized, hey, these geomagnetic storms, which at that time they knew was caused by the sun. By 1921, they knew that this geomagnetic storm had been associated with the flares visible on the sun a couple days earlier. And they put it all together and realized the solar flares, the solar eruptions, and these geomagnetic storms can really be a threat to Earth-based technologies.
And even more recently, 1989 in Quebec.
Yeah, that was another big one. Not quite as big as 21. So I like to say that even 1989 was not as big as 1921, but it was more noticeable because we had more technology. We had more vulnerable power grids. We had, in that case, there was a interruption again and disruption of telephone cable systems. They noticed large currents on pipeline systems. Now you have long distance pipelines, which can get 1,000 volts across them, causing currents which eventually erode them. So the more technology we build up, the more and more we realize we're potentially vulnerable to these space weather events. And one thing I like to point out is, as you said earlier, orbital space is becoming more and more crowded. I think everybody knows the number of satellites in low Earth orbit in 1921 was pretty small, probably pretty close to zero. And so we've gone from, that was really the last time we've had what we would classify as superstorm. 89 was also close, but 1921 was a really big one. If that happened today with all the spacecraft we now have in low Earth orbit having to deal with this incredible disruption in their orbital trajectories, I think we'd be in for a very interesting couple of days.
So we've talked a little bit about the impact and prediction, and hopefully we are getting better at it, and hopefully we will continue to get better at our predictions. What about mitigation? So what can we do about both our technology in orbit as well as the risks that it poses to us down here on good old Earth?
Yeah, the good news is that since 1989, the power grid companies have become very aware of the potential impact of geomagnetic storms. So they've put in some protective systems. They're aware of the potential impact. And the other good news about that is the geomagnetic storm impact, because it's caused by the CME kind of rumbling across space, is the one thing we can give a significant warning to operators about. We can't warn about flares because we don't know when the eruptions are going to occur on the sun, and they occur and we see the photons immediately. We can't warn too well about the radiation effects because those come so quickly. But the CME, we can give when we see a large eruption on the right part of the sun, in other words, pointed at Earth, we see those eruptions occur. We can see the plasma cloud coming off the sun in our coronagraph instrumentation. We can give power grid operators, 10-hour warning or something like that maybe on the outside or the inside case. The fastest CME we've ever recorded from the sun to the Earth was 14 hours. That was a 1972 event, actually, which also had a huge radiation storm associated with it. So we've got, the possibility of giving 14 to 24-hour warnings to the power grid, in which case they can do things like raise the level of activity on the grid so that it's less susceptible to these large fluctuations. Unfortunately, that's sort of the best news we have. The orbital situation is much more complex. We don't really have good models for how much the atmosphere is going to heat up and expand, and how much drag that's going to cause on the satellite infrastructure, and how much they're going to move. And so while we can give them a heads up that, hey, there's a CME coming in that's going to heat the atmosphere tremendously, we don't really have good tools or models yet that tell them this is what you can expect your satellite to do. And that's one of the main things we're working on in this new Space Weather Center that we just got inaugurated here at CU and University of Michigan, University of Iowa, and the National Center for Atmospheric Research. So we're all working on that as a main focus. Can we get a better model to tell the satellite operators really what they're going to be flying through in one of these extreme storms? And then perhaps they can take mitigating actions like planning for thrust maneuvers to keep their altitude up, or, at the very least, repointing their communications antennas so that they know to look, 5, 10, 15, 20 seconds ahead of where the satellite normally would be to try and catch it, talk to it. But there's a lot of work to do there.
Well, it's time for us to start wrapping up here, quickly wrapping up, unfortunately. However, one final thing, is there any advice that you can provide to folks that are currently perhaps in various studies in physics at some point in their academics, who are thinking about where they might want to go into a field in science? Perhaps it's a space weather person in the future. Maybe we'll have people doing traffic and space weather in our morning reports, but that would be interesting. But how about for people who are thinking about research, especially at the convergence point of AI and heliophysics, and where should they aim right now, or think about aiming?
Well, I do like to say that data science is the new calculus. And so if you are studying physics and math, applied math in college or graduate school, it's imperative that you become really aware and educated of the power of artificial intelligence and machine learning, scientific machine learning in particular, the sort of subfield which is applying data-driven methods to complex nonlinear dynamical systems like the atmosphere, like the sun, to try and predict these systems better. So learning, if you're going to go towards the field of space weather, again, with that major term of prediction attached to it, not just studying the phenomenon, not just simulating the phenomenon with models, but actually predicting this complex nonlinear dynamical system, it's imperative to really grab onto that AI ML rein and hold on to it and ride the ride, because I think it's going to be, again, I think it's going to be how science is done going forward, at least when you have the task of predicting a complex system. And with that, we also have to keep in mind that people are going back to the moon. We hope that people are going to Mars as well. I think that's one of the greatest adventures in human history, if we can make that happen. And if you're going to be out there, that's the same thing as flying from New York to Tokyo. You better know the weather all the way along the route. Otherwise, there can be serious consequences, right? So space weather, I believe, is going to have to be integrated into the space travel that we're planning to do. Even the moon, it's outside the magnetosphere. So you better know what the sun is doing at all times in order to, at least give yourself some warning of the potential radiation storms that the sun can unleash. And on Mars, there is no protective magnetic field. So it all comes.
It's a big deal. It's a big deal for us. Okay, thank you. If you're interested in learning more about what FDL has been doing in its work with NASA and ESA over the last 7 years. Go to fdl.ai and you'll be able to find that. And Tom, where can people go to learn more about what you guys are up to in Boulder with regards to space weather?
Spaceweather.colorado.edu is our website.
Love it. Thank you. And Tom, thank you so much. It's just always so wonderful to spend time with you in discussion, and I'm sure those listening feel the same way. And we look forward to doing more of that with you, in addition to our many future collaborations that we have planned. Thanks for joining us, Tom.
Thank you so much, Jonathan, and thank you to FDL too. It's a great organization.
Thank you. And thank you to those of you who've joined us, and we hope you join us next time for The Wormhole as we talk with Dr. Anna Youngbluth. She is a research fellow at the European Space Agency, focused on the role that the Sun-Earth system plays in long-term climate here on Earth. Thanks for joining us. We'll see you next time.